Hello students, in the last lecture we did the Lorentz force, that is when a charged particle was moving in the presence of both electric and the magnetic field. So the electric force plus magnetic force gives the resultant force which was known as a Lorentz force. Also sometime if the electric field is not there, that is E is equal to 0, we will refer or we will call the magnetic force to be the Lorentz force. So if there is no electric field and we are discussing only about the magnetic field, so in some situation we may call the magnetic force as a Lorentz force because there is no electric field, so Fe is equal to 0. Now in this topic 4.2.3, we will find out the magnetic force on a current carrying conductor. Now we know that if any charged particle, that we have already studied, that if any charged particle Q moving with the speed or velocity v vector in the magnetic field B vector, then the magnetic force act on it, and the magnetic force was given by the formula Q v cross B vector. And using the right hand screw rule, we found that the force is perpendicular to the plane containing V and B. This is the formula when any charged particle, say a proton or electron, enters into a magnetic field. Suppose now we have a current carrying conductor. So we consider one conductor carrying current I, and that current carrying conductor is placed in an external magnetic field. However, we have also seen in the first lecture that if a wire carry a current I, then using a thumb rule we found a space or a region around it which was referred as a magnetic field. In this situation, we are taking the magnetic field which is external. So the current carrying conductor also produce a magnetic field. So in this expression, the magnetic field is not the field produced by a current carrying wire, but here a current carrying wire or a conductor is placed in an external magnetic field which is given to us. So let us consider a conductor. So to understand this, let us consider a conductor having the cross-sectional area A. So this is the cross-sectional area. We are taking a conductor to be quite thick, otherwise we have to take a wire having a small cross-sectional area carrying current I. Let the current I is flowing in a wire in an upward direction. Now we know that in third chapter the current is due to the motion of the electron. So current I is produced due to motion of electrons. So electrons are the mobile charge carrier. Now the motion of this electron is in opposite direction to the conventional current. So if the conventional current is in the upward direction, the electron are moving in a downward direction. So the mobile charge carriers are electrons. Here the mobile charge carrier is electrons. So it means now this number of electrons, this was a formula for, say, a one electron is moving in a magnetic field. In this situation, there are number of electrons which are moving in a magnetic field. Let us assume that the magnetic field is along the x-axis. So let us consider this situation. Now I have to find out the resultant force acting on this wire. The experiment was done by the Ampere, and he said whenever you place a wire carrying current I in a magnetic field, it will experience a force. Again, the force is perpendicular to the plane containing I and B vector. So in the end, we will again apply the right hand screw rule or a thumb rule to find out the direction of the magnetic force. Now since we are not discussing or we are not considering any electric field, we call this magnetic force as a Lorentz force. Now let us say current I, a wire carrying current I, wire carrying current I is placed in magnetic field B vector. Now if we consider, or if I want to find out the total number of the charge, so either I say in actual practice it is the motion of the electron due to which the current is produced, but here we will refer it as a charge. So if electrons are moving in a downward direction, then the positive charge are moving in the upward direction, though we know that positive charge does not flow. But the conventional current was given by the Benjamin Franklin's concept, where he considered that a current is due to the motion of the positive charge particle, because electron was discovered recently or very late as compared to the discovery of a proton. So we will refer in our theory as the motion of an electron to be a motion of a charge. Now in chapter 3, and you remember, it is the electron density, or we call it a number density. So n, let n be the number density. See, I have to find out the total force acting on it, on this entire wire. So I have to find out the total number of charge flowing in this wire, because the entire wire is kept in the magnetic field. So let us find out total number of charges flowing in the conductor. So n is a number density, and if we know the formula, n was equal to the number of charge, the total number of charge per unit volume, and this implies the total charge n is equal to n into V. Now let us say the length of a conductor is L. So let L be the length of a conductor, then capital N is equal to N. Volume can be written as area into length. So this is our question number 1. Now if the force acting on a single charge particle is QV cross B, then the total force acting on n charges will be equal to NaL multiplied by this. So this is the force acting on a single charge. We have total n, so NQ. In the place of capital N, I will write NaL. Now here, this V, in this situation, V was the velocity of a charged particle, which was a single particle. Here we have number of charged particles. So we assume V to be an average drift velocity. We know the concept of a drift velocity. Drift velocity was the average velocity by which an electron was drifted from one end to another end in the presence of an electric field. So we assume Vd to be average drift velocity of the total charge N. Therefore, the Lorentz force, or in fact you can also call it a magnetic force, the Lorentz force F is equal to, now if we apply the concept of the quantization also, that is Q is equal to Ne. Here we call Q as a single charge. So if we have a N charge, I can write NaL Vd cross B. So this is the formula for the force acting on a wire carrying current I. But we have to derive this formula in the terms of current I. Now from the third chapter, we define a new quantity which we called a current density. And if you remember, the current density J was equal to I upon A, and J was also equal to NeVd. Here there will be one Q also, total charge into Q. So total N into Q. Now J was N, EVd. Here we have given this charge as Q. If it is an electron, we will substitute a E value. In fact, it is the motion of an electron only which produces a current I. But we call it a charge Q here. So J was equal to NQVd. Therefore, F vector can be written as, now in the place of NQVd, I can write J. So it is AL J vector cross B vector. This is in the terms of the current density. Now J is equal to I upon A, or J multiplied by A can be written as I. So now you have to shift this vector, J vector. Current density is a vector quantity, but current is a scalar quantity. Here the arrow was on the drift velocity. Drift velocity is in the downward direction. Here the drift velocity is in the downward direction if we consider the motion of the electron, or in fact here we call it a motion of a charge. Now current density, this arrow, first we replace J vector into A as an I, and in the vector form F is equal to I L vector cross B vector. Now what I did here is, we have shifted this vector to the length of a wire, and this direction of this length is in the direction of the current. So we need to shift this vector from a drift velocity. It was shifted to J vector. Now J vector is equal to I upon A vector, and if you remember, this A vector will be the area vector. It will be taken in the direction of the current. So indirectly, this vector sign from Vd was shifted to A vector, or you say it a J vector, because whatever is the direction of a vector, it will be the direction of a J vector, because I is a scalar quantity but current density is a vector quantity. So we shifted this vector to J vector. Now I have to replace this J vector into A. So I shifted this arrow to the length, because the length is taken in the direction of the current, or the length is taken along the area vector. So the total Lorentz force acting on a wire is IL cross B. So this is the magnetic force. This will be referred as a magnetic force. Sometimes we call it a Lorentz force. This magnetic force acts on any current carrying conductor, and by applying the right hand screw rule, you can find out the direction. So in this situation, if I see this situation, I is in the upward direction, so the direction of length will also be taken along the y-axis say, and the magnetic field is along the x-axis. So we talk about the direction. This can be written as IL j cap cross B into I cap, and j cross I is equal to k. So this formula becomes BIL bill K cap. It means when I place this wire in which the current is flowing upward in a magnetic field B vector, then this wire will be moving, or the force act on this wire along the z axis. So you apply the right hand screw rule. So if I keep a screw at this point, so let us keep this screw, let us take this as a I, this is B. I keep a screw perpendicular to this. I have to do L cross B. So L direction will be taken in the direction of the current. This will fall like this. So L cross B. So you have to move like this. So it will be J cross I. J cross I. It will be, it should be minus K. So if I apply this, this is my J cap, I cap, screw is tight, or if I see the head, it is a clockwise direction. So the screw goes into the plane of the board inward, that is say minus Z axis. So this is how you apply the right hand screw rule, or you can apply the right hand thumb rule. I take this palm perpendicular to the plane containing I and B, and I have to curl my hand from L to B. My thumb will be inward, so the force acting on the wire will be inward. So if the magnetic field is along the x-axis, and if I place a wire carrying current, it will move inward. You have to remember that this B is the external field. This B is the external magnetic field, and not the magnetic field produced by a current carrying wire. So this is the Lorentz force, or you can say the magnetic force on a current carrying wire. Now here, while deriving this, we have considered the wire to be straight and the magnetic field, let us take an example, is taken along the x-axis. Now suppose the wire is an arbitrary shape, that is not linear, it is not a straight. So this is a wire and the current is flowing through it, and again such wire is placed in a uniform magnetic field. So if we assume that the wire is arbitrary shape, not a straight line, then the step is we divide this small wire, this entire wire into the small elements, and one element, that is, if you remember in first chapter, if we divide a wire into a small element, it was called as a line element. Here each element carries a current I, so each element will be referred as the current element or a current line element. So if the wire is a straight line, then we have the direction of I as J cap and direction of B as an I, and you can apply the cross product. But if the wire is arbitrary shape, so we consider any element, say this is a ith element, then the force acting on ith element can be written as dF is equal to IL I cross B vector. So instead of L, we write it DLI. That is a ith element. So first current element, second, third, there are infinite elements. Now if there are infinite line elements, this equation can be written as summation I dli cross b, where I is running from 1 to n. And if I is running from 1 to infinite, then this equation can also be written in the integration form, that is I dl cross b vector, that is a line integration. So if the wire is a straight wire, we can directly apply the formula IL cross B. If the wire is an arbitrary shape, we divide this wire into a small element. Each element will be referred as a current element. We find a force on small current element. If the number of the current elements are n, so I can do a summation, or if the elements are infinite, then that summation is converted into a integration, which will give us the total magnetic force on a current carrying conductor. Now let us move to a new topic 4.3, that is motion in a magnetic field. So we have studied that when a charged particle enters into a magnetic field moving with the velocity v, the magnetic force was given by q v cross b vector. Now we will further investigate the motion in detail. Now before moving to this topic, we know that in mechanics, so in standard 11th we have studied that if I apply a force on any particle or a body in the direction of its motion, suppose the body is moving along the x-axis, and if I apply the force on it in the direction of its motion, so body is already moving along the x-axis and I apply the force on it, so the work done will be given by Fd cos of 0, that is the formula for the work was F dot D. In this case, the work is done on the body. So I will say the work is done on the body due to external force F. Similarly, here the component is in the direction of the motion of an object. Suppose the object is moving and the force is applied opposite to it. The force is applied opposite to it. Then W can be written as Fd cos of 180 degree. So that is equal to minus Fd. That is, the work is done against the motion of an object. That is, the work done is opposite to the direction of the motion of a particle. So whenever we have a component of force either in the direction of the motion of a particle, or whenever the force is or the component of force is in a direction opposite to its motion, the work is done on a particle. But there was also a situation where the force was perpendicular to the displacement, and we know that if the force is perpendicular to the displacement, then the work done comes out to be 0. That is, no work is done on the body. Now let us see what will happen if a charged particle enters perpendicular to the magnetic field. So in that situation, we have done the cases where the force was given by Q V cross B. Now the direction of V is in the direction of the displacement, or we can say whatever is the direction of a displacement, that is the direction of V. And F, the magnetic force, that is magnetic force was given by Fm is equal to Q V cross B. This F is always perpendicular to V. This F is always perpendicular to the V. It means now V direction is same as the direction of the motion of a particle. It means the force and displacement are perpendicular to each other. So when a charged particle enters perpendicular to the magnetic field, the work done or the force acting on it is maximum, but the work done comes out to be zero. So we have studied this case where the particle is entering perpendicular to the magnetic field, and in that situation we have written the point that it will perform uniform circular motion. Now we will see how it perform a uniform circular motion. So whenever a particle enters perpendicular to the magnetic field, the force acting on it is maximum because theta is 90, sin 90 is 1. But what about the work? Now F is always perpendicular to V, or you can say F is perpendicular to B. So if I say what is the angle between F and V, it is 90. What is the direction of the displacement? That is the direction of the velocity. So what is the angle between the force and displacement? It is 90. So work done is 0. It means whenever a charged particle enters perpendicular to the magnetic field, no work is done on it. There is no transfer of energy, though the momentum will keep on changing, or the speed of an object or a particle will remain constant, but its velocity keeps on changing continuously and it will perform a circular motion. Now let us see how it happens. Consider a magnetic field going into the plane of the board. So this is the magnetic field represented by cross. It means the magnetic field is going into the plane of the paper, or here it is a plane of a board. So this is a plane, or you can say the B vector. Let us take this as negative z axis, that is minus k cap. Now magnetic field is inward. So this is magnetic field. Now let us say a charged particle enter perpendicular to it. So this is the direction of the motion, that is a displacement or a velocity. Now we apply this rule and we will find out the direction of the force. It is quite clear that a force will be perpendicular to B and V vector. So I have to apply V cross B. So if this is the situation, this is my V, thumb is upward. So the force acting on the particle is in the upward direction. So instead of moving in a straight line, the particle at that instant will move upward. Again, this is in the magnetic field. Again we apply the right hand screw rule. Again we apply the right hand screw rule. At every instant, if we apply a right hand screw rule, we will find that this particle will perform a uniform circular motion where the force will be always perpendicular to the V vector, and therefore the work done will be 0, and the particle is performing uniform circular motion means its velocity changes continuously, or at every instant its velocity changes but speed remains constant. There is a change in the momentum because momentum is mass into the velocity. So let us say the particle enters perpendicular to it. This is V vector. So let us take V vector in the first case, or a first instant where the V vector is I cap. So this is its original path of motion. If the magnetic field is not present, the particle should move in a straight line. But because the magnetic field is present, I apply this law, so it becomes I cross minus k. Let us draw the direction. This is I, J and K. So this is how we apply the cross product. So I cross k, that is minus j. Already we have minus. So the direction comes out to be Fm comes out to be jk. So the particle, instead of moving in a straight line, it will move in the upward direction. So this is the instant where the particle has changed its direction from I cap to j cap. So this is B going into the plane of paper or a plane of board. This is V. So this V, or the particle, charged particle, will move in a straight line if magnetic field is not present. But due to the presence of an electric field, the magnetic force acts on and it will move upward. Now the velocity is upward. So in the second case, this is the second instant where V vector becomes j cap. Now again, if I apply this formula here, it becomes j cap cross minus k cap. Now j cross k, it is I and we have a minus sign. So again, Fm comes out to be minus I. It means now the particle should change its motion in this direction. So the particle, this is the magnetic field going into inward. As soon as it entered the magnetic field, the force acting on it at that instant, now this force acts at each and every instant, at each and every point. So this particle, instead of going upward, along the x-axis, it moves along j. Instead of moving along the j, it comes to minus I. And again I apply this formula. Now at the third instant, V becomes minus I cap. So in the third instant, it becomes minus I cap into minus k cap. That is minus minus becomes plus. So I cross k. So I cross k, that is minus j. So it comes downward. So in the third instant, the force will immediately change to minus j. So if I apply this, or if I draw this diagram, what will happen? As soon as the charged particle enters the magnetic field, it will perform a circular motion, or the path becomes curved in this case. So if I complete this, if there is a magnetic field all around, the particle will perform a uniform circular motion. Let us draw this diagram at this point. This is the situation where we apply a right hand screw rule at each and every instant. So whenever a charged particle enters perpendicular to the magnetic field, at every instant the force acts on it and the path becomes circular. So let us see this first situation at this point. Now let us understand this diagram again. So this is the first instant. Let us take this instant. This is V vector. B is going into the plane of paper. What is the direction of the force? That is J. Now V becomes J. New direction becomes J. This is V vector. What is the direction of force? Minus I. So this is F vector. You say it a Lorentz force. We are not talking about electric field, so we call it a Lorentz force. Then this is minus I. Now V becomes minus I. So let us consider this point. This is V vector. What is the direction of the magnetic force? J. Now if we continue this, now this is at the fourth instant, V becomes minus J. Again V. So your F, if you say use this, that is minus J cross minus K, again this minus minus gone, J cross K it becomes I, or now it should be clear that the force is perpendicular to the V, and therefore we also know this, that in uniform circular motion, whenever a particle perform a uniform circular motion, its speed remains constant, velocity changes at each and every instant, that is, the momentum will change but the speed remains constant. And what about the work done on a charged particle? Work done is zero. So this is the conclusion, where we found that whenever a charged particle enters perpendicular to the magnetic field, there is no transfer of energy because no work is done. You have to remember, the work is done only when the force or the component of force is in the direction of the motion, or it is opposite, or it makes an any angle theta. But if the force and the displacement are perpendicular to each other, the work comes out to be zero. In this situation, we are not considering the displacement, but we know the direction of the velocity is same as that of a displacement at any instant. So here, if I say the particle enter perpendicular to the magnetic field at each and every instant, the force should be perpendicular to the V vector. It should be clear that this F, now we call it a Lorentz force, it is actually a magnetic force. So this magnetic force is always perpendicular to the V vector as well as B vector. And since F vector is perpendicular to the V vector, the work done comes out to be zero. If work done is zero, the energy is zero. That is, no transfer of energy take place. So let us immediately write down the conclusion. Number first conclusion is, when a charged particle enters perpendicularly to magnetic field, then it performs uniform circular motion. This is about the path followed by the charged particle. Second conclusion, which is important in this situation, so we assume that a charged particle enters perpendicular, then F is perpendicular to V vector. That is, work done comes out to be zero. Third, speed remains constant. Velocity, and in fact we say momentum, changes. Fourth, since it is performing a uniform circular motion, the direction of the force is towards the center. So the direction of F vector, or a Lorentz force, is towards the center of circular path. And we know that the force which is directed towards the center is a centripetal force. So here the necessary centripetal force is provided by the magnetic field. So whenever a charged particle enters perpendicular to the magnetic field, it performs uniform circular motion, and the necessary centripetal force which keeps the body in circular path, that should be, or it is provided by the magnetic field. If the magnetic field is not present, then we know that at any instant this particle will move along the tangent. It is similar to that a stone tied to the string is willed. So if we will it, and if I leave that stone will move tangentially. So if the magnetic field is removed, and if the particle is moving in a circular motion, at any instant it will be moving along the tangent. So wherever we switch off this magnetic field or if we remove the magnetic field. So this is the conclusion you have to remember. This is an important property, that no work is done. In fact, there is no transfer of energy, but there is a change in momentum. Now in the case of the electric field intensity, if a charged particle enters into the electric field, then there is a transfer of energy as well as a momentum, because when the charged particle Q enters into electric field, again we know the force formula is simply Q into E. So force act on it, and if the component is in the direction of the motion or opposite, the work is done on a charged particle due to electric field. While in this situation, the work done is 0. But if a charged particle enters only in an electric field, the work is being done on it. That work done give rise to the potential or potential energy that we have seen. So work is done in that case. So there is a transfer of energy as well as there is a transfer of momentum. In this situation, no work is done. There is no transfer of energy, simply because the work done is 0, the speed remains constant, velocity, that is the direction, or the momentum changes continuously. The force at any instant is perpendicular to V vector. So these are the conclusion. Now in the next lecture, we will see that this necessary centripetal force is provided by the magnetic force. So the centripetal force, we know the formula, that is mv square upon r, and it should be equal to the magnetic force, because due to the magnetic force or due to the presence of the magnetic field, this particle is forced to move in a circular path. So necessary centripetal force will be provided by the magnetic force. So when it performs a circular motion, we can derive the formula for the radius, what will be the radius of the circular path, as well as we will find out what is the angular speed, what is its frequency, and what is periodic time. Here we have considered a simple case where the particles enter perpendicular, and in the previous lecture we have discussed that if the particle enters in the direction of the field or in the direction opposite to the field, that will be theta is equal to 0 or 180 degree, then the force acting is 0. So we started with this angle to be 90. Also we will see if this angle between V and B vector is not 90, what will be the trajectory of the particle. So if theta is 0 or 180 degree, the path followed is a straight line or the original path. The magnetic field will not deflect the charged particle, so its direction of motion will not change. Suppose the particle enter perpendicular to it move into the board, or it come out from the plane of the board, that is 180 degree or 0 degree, then no magnetic force will act, so the a charged particle will not be deflected. And here, when it enters perpendicular, it is deflected at each and every instant. These few instants are being shown to understand clearly how it performs a uniform circular motion. If I take this instant, this will be the velocity along the tangent, but force will be always 90 degree, that is perpendicular, and this force will be directed towards the center. So in the next lecture, we will find out the radius of this circular path, angular frequency, and the periodic time. Have a nice day.